System type is another metric to uh, look at the performance of control systems. System type essentially allows you to classify different systems based on how they respond to inputs of different polynomial, time polynomial order. So system type is the highest order Q of the input time domain polynomial such that the steady state error is a non-zero constant. So definition, the order of a time domain polynomial is the highest power of the time t. So for example, here u of t is a0 plus a1t plus a2t squared. Since the highest power of t in this input polynomial is 2, the order of this polynomial is 2. Now if you send this input to a system and you get a non-zero constant as steady state error, then the system type is 2. System type can be defined both for reference input as well as all disturbance inputs. These are the implications of system type. If a system is of type Q, and to this system if you give an input polynomial of the order q minus 1, it will result in 0 steady state error. If you give it an input polynomial of order q, it will result in a non-zero constant steady state error. On the other hand, if you have an input polynomial of q plus 1, it will result in an infinite steady state error. So if I say my system is of type as 0, q equal to 0, then if you give it an impulse input, which is order q minus 1, which is minus 1, it will result in a 0 steady state error. If you give it a step input q equal to 1, it will result in a non-zero constant steady state error. If you give it a ramp input, then you'll get infinite steady state error. Now let's look at an example here. This is your control system. R is the reference input. You're looking at steady state errors, therefore you need the error. WA is the disturbance input. That's the actuator disturbance. The error signal in terms of the reference input is this. You've derived this many times. If the reference input is a time domain polynomial of order q, then the Laplace of r of small r of t, which is capital R, is going to be 1 divided by s to the power of q plus 1. Substitute that in the error equation, and then we find what steady state error is. Steady state error is limit as s tends to 0 s e of s. We substitute everything here. Now this s cancels with one of these s's here, so this is what you get. I take this s inside the brackets and substitute for d and g here. This is what I get. Now this s squared cancels with two of these s's here, so this becomes s to the power of q minus 2. Now let's say q equal to 0. No, I mean q equal to 2. So if q equal to 2 and I let s go to 0, now 2 minus 2 is 0. So s to the power of 0 is 1. Now then this drops to becomes s squared, since q equal to 2, and if you substitute s equal to 0, this becomes 0. This is 0, this is 0. Therefore you get a non-zero constant. Since the steady state error is a non-zero constant and q equal to 2, the system type is 2. In summary, we need to understand sensitivity, understand the definition, understand how to derive it for various functions. We've covered it. You do the closed loop transfer function, you can find the steady state error, you can find time to rise, time to settle, so on and so forth. Find the function, you need to do the derivatives and derive this. Tracking and disturbance rejection, you need to understand that tracking is with respect to reference input only. Disturbance rejection can be computed with respect to various disturbance inputs. You analyze one input at a time by setting all other inputs to 0. And for system type, you need to understand the definition and you need to understand how to derive these expressions. And that's the end of this lecture.